Hello, folks. So we're talking about number 46 from the back of the chapter. This one is all about angular momentum. So we have a 2 kilogram, 20 centimeter diameter turntable that rotates at 100 RPM, rotations per minute, on a frictionless bearing. All right. We have two 500-gram blocks that fall from above, hit the turntable simultaneously at opposite ends of a diameter, and stick to the turntable. What is the turntable's angular velocity in RPM just after this event? I don't love that we keep talking about RPM. I really wish we were just doing radians per second, but I'll do a quick conversion at the beginning and then skip the conversion at the end, just to get things going here. All right. So to begin with, right, we have this rotating turntable. You should think of it just as a disc, right? Just a disc rotating. And if I think about this disc rotating, and if I think about curling my fingers in the direction of the rotation, right, I actually see that I'm going to have this maybe I'll do it in red here. I have an angular momentum vector pointing straight up. This is going to be important for us as we think about the conservation of angular momentum here. But let's go back to quick solving for omega I. Omega I we know is 100 RPM, but that's a little cumbersome to work with. It's not our SI units. I need to turn these rotations into radians by saying, by multiplying, right, 2 pi radians per rotation, per one rotation. So that's going to take care of the R here. And then I have minutes. I got to go into seconds. So I have per minute, so 1 over minutes. That means I need to have a minute up here, and that gives me 60 seconds down here, right? And so the final amount, if we multiply this through, is 10.5 radians per second. All right, so that's my initial angular velocity of my disk. Now, I do have these blocks coming down. They're going to come down and they're going to hit. They have some R here, some R, and if I think about the momentum that they initially have, they have some initial momentum this way, P or V if I want to think about it that way. And if I think about R cross V, R cross P, right, I'm going to have my, extend my R vector out this way. R cross P gives me something that points kind of tangent to this circle this way, right? Let's clear up this picture just slightly. It's going to be, perpendicular to these three things. It's going to be pointing this way, out of the page, essentially, out of the page. I'll try and just draw that. So this is the L of our block. Yes, we actually do have some angular momentum of this thing, even though it's moving just in a straight path. Remember that L is strictly defined as R cross P. So if I have some R and I have some P, I do have some angular momentum, right? But notice how our L of the disk and L of the block are perpendicular to one another, right? L of the block, or blocks I really should say, is perpendicular to L of our disk. So what happens to L of the block? Well, L of the block is absorbed. It's actually not conserved. I should say it's not conserved unless you look at a global system. This is absorbed by the axle, right? The axle, or the bearing here, absorbs the angular momentum. This is a non-isolated collision when we think about it in this direction, right? I have an impulse, right? I have some sort of impulse that is mediated by this bearing, this axle here. When I think about this, right, this is conserved. This angular momentum of the disk has to be conserved because there's no external forces by a complex external system from the environment, right? Of course, I have these forces between the block and the disk, but those are equal and opposite. Those are interaction forces. So when we say that these two things are perpendicular, what we're saying is that they don't influence each other. They don't influence each other. So really, I'm just thinking about what I have initially, which is my disk, right? It's I of the disk times omega I. That is my initial angular momentum. And since we're only considering the angular momentum going up or down, we're just going to leave out any vector hats. So now I have equal to LF, right, which is now I of the disk plus I of my blocks, let's call them blocks, times the shared omega F. What we have here is a perfectly inelastic collision, but we're conserving angular momentum this time. So, when we think about what we have initially, I of the disk, well, a disk has an I of 1/2 mr squared times omega I, which we have, equals the same 1/2 mr squared, plus, now I need to worry about what the I of the blocks are. When I think about just a particle, orbiting around a point, right, I'm just thinking about that initial general definition that I of any sort of system is equal to mr squared summed up over all these things. So I just have a point particle essentially that is r away, and I have two of these things, and they have some little m mass, and so this is the I of the blocks, right? Little m times r squared, and then we have two of them, right? Because we have two blocks, times omega f. So that's what we're looking for. If I work through this, right, I'm going to see that I have 1/2. Let's start plugging in some numbers. 2 kilograms times my 0.1. Let's make sure. Yep, 20 centimeter diameter, so 0.1 meter squared times 10.5 radians per second, all over 1/2 2 kilograms times 0.1 meters squared plus 2 times 0.5 kilograms times my r squared, which is still 0.1 meters squared. And that should give me my omega f. Now, if you left this in RPM, you actually would still get an RPM coming out of it. But we really do want to always think about using SI units. So I wouldn't give you, hopefully would I think this stuff is hard enough without having to put unnecessary conversions in, honestly. When you find what omega f is, when you calculate that, you get 5.25 radians per second. Another way of saying that is about 50 RPM. 50 RPM. And that makes sense. So we started at 100 RPM, right? We started at 100 RPM. We added 50% of its mass to it, right? We added that in the addition of the blocks and how far they are, right, relative to the point of rotation, and we've slowed things down. Again, I can change. Mass generally in a collision doesn't change if we're thinking about linear momentum. Mass doesn't really change. The system has to be the system, right? The system initial has to be the system final. But when we think about collisions and things are rotating, the moment of inertia can totally change. It can totally change during the collision. It's not because the mass is changing per se, right? The mass is not involved initially, right? That's why we're not even considering it, because we're thinking about this direction of angular momentum. These masses do have angular momentum, but it's pointed in a perpendicular direction. So the masses just don't even contribute initially. I should say the blocks don't initially contribute any angular momentum initially, and then we add them to the spinning system, right? We change the distribution of mass in the system, and bada boom, we now have a change in our moment of inertia. So this is a quick example just showing how a collision here can change our moments of inertia, but we still need to conserve our angular momentum. That's going to do it for this one. If you have any questions, again, feel free to email me or swing into an office hour. I would definitely consider looking at the other angular momentum instructional problem, which should be a video solution of that should be up a little bit later this week. But it's another good problem to kind of wrap your head around: angular momentum. All right, have a good one.